Adam missed it anyway.
Huh?
Oh, and Adam, you said you didn't have much trig, did you?
Yeah, but I'm practicing. So.
You've been practicing? Okay.
But I don't really know about that. Keeps taking my pencils. Kirby? No, keeps stealing stuff.
So this is not exactly in chapter 12. We are going to start chapter 12 today, but this is something that there are some problems in chapter 12 that talk about polar coordinates, and it's extremely important in chapter 13. So like I said, it's stuff, once you see the conversion formulas and once we start talking about it, hopefully it'll seem familiar. It'll seem like we've done this before. If you took Math 172 here, we do talk about polar coordinates in Math 172. And then all the conversion formulas are going to be familiar because it's the exact same conversion formulas that we use to go back and forth with vectors to change between component form and magnitude and direction format with vectors. Okay? So polar coordinates, they're just another way to locate a point in the XY plane. We usually use Cartesian coordinates, which are X and Y coordinates. So this point right here, I could get there by going a certain number of units on the x-axis and then a certain number of units on the y-axis, and those form a rectangle. So that's why we call them rectangular coordinates. Right. Polar coordinates, you are going to go straight to that point from the origin on a particular angle. So it's still the exact same point, but it doesn't make a rectangle. It makes a triangle, or it makes an angle. So it's the exact same point, but it's represented by two different numbers. So let me go back to black. So this is X, and this is Y. It's how, the X is how far left or right we need to move. The Y is how far up or down we need to move to get to the point. We can get to the exact same point. So our theta is not a different spot. It's just a different way to get to the same spot. So I can get to the same exact spot, but I would go directly there from the origin, R units at an angle of theta. So if we pull this information out of the plane, it's just a triangle. It's just a right triangle, and it's the exact same information that we used when we talked about vectors. There are two legs, X and Y, which are just like the components for a vector. And then we have our hypotenuse and our angle, which is just like the magnitude and the direction for the vector. And this takes us from 0, 0 out to this other point, which we could write two different ways, either xy or r theta, depending on which coordinate system we were using. There are some equations that are much easier to write in terms of r and theta than they are in x and y. And there's some equations that are much easier to write in terms of x and y than they are in terms of r and theta. So there are advantages to knowing both systems. So converting between the two systems is just right triangle trigonometry stuff. It's stuff that we've already done. The relationship between x, y, and r is just sides of a right triangle, so that's going to be Pythagorean identity. R is the hypotenuse, where x and y are the legs. Theta, if we know x and y and we're trying to get r and theta, for theta, if we know x and y, we're going to use tangent, because x and y are opposite and adjacent. So we're going to do tan inverse of y over x. You need to be careful, though, and I try to remind you this every single time, you need to be really careful about what quadrant that point is in, because your calculator doesn't always give you back the correct answer for tan inverse. The calculator uses quadrant 1 for positive values and quadrant 4 for negative values. The calculator won't ever give you back a quadrant 2 or quadrant 3 answer. So if you know your point's in quadrant 2 or quadrant 3, you're going to have to move that answer to quadrant 2, quadrant 3 yourself. These are the exact same formulas we used back at the beginning of 11 with vectors to get magnitude and angle for a vector when we knew its components. And then if we know magnitude and angle and we want to turn it back into, or if we know polar coordinates and we want to turn it back into rectangular coordinates, so we know r and theta and we want to turn it back into x and y, x equals r cosine theta, y equals r sine theta. And again, those are the exact same conversion formulas we used back at the beginning of chapter 11. And we could use these conversion formulas to change just a single point or to change an entire equation. So we're going to just convert a couple of points to start with. We're going to convert from rectangular to polar. And when we write theta, we're also going to learn later on another coordinate system that's similar in 3 dimensions. The angles are typically represented in radians. We usually don't use degrees here. Okay. I would still use degrees so we can get an exact answer. Because if you put your calculator in radians, your calculator is always going to give some crazy decimal. So I would still keep your calculator in degrees so you can get an exact answer if there is one. And then we'll try to convert that exact degree measure over to a radian. So you're going to have to read directions on these to know what they gave you. So they tell us convert it from rectangular to polar. So negative 3, 3, that's an x and a y. And they want an r and a theta. And it might be helpful to plot that point to see exactly where it is, because the quadrant for theta is going to be important when we do the tan inverse. What quadrant is negative 3, 3 in? It's in quadrant 2, right? Because negative 3 is going to take us left 3, and then positive 3 is going to take us up 3. That's going to be quadrant 2. So in terms of rectangular coordinates, negative 3, 3 is in quadrant 2. So we can also get to that exact same spot. Instead of thinking it as 2 steps, an up and a left, we could just go directly there from the origin, but we just have to say how far and at what angle. So from the origin, we need to say how far that is, and we have to say at what angle. Yes. And then also convert to radians.
Well, you take 180 and subtract whatever.
There's a couple ways you can do it. The calculator is going to give you a negative number.
Oh, I got you. Okay.
So either way. If it's in quadrant 4, it depends what the instructions say. You could leave it as a negative angle, or you could add 360 if they want it as a positive angle. So let's see what this distance is. That's really just the hypotenuse for the right triangle that has sides of length 3, 2 legs of length 3.
So is R kind of like the magnitude?
Yeah. R is just the magnitude of the vector that has components that are both 3. It's 3 root 2. We're not going to change it to a decimal, but we are going to simplify it to 3 root 2. And then for theta, we do tan inverse of the y over the x, which ends up being tan inverse of negative 1. I would keep your calculator in degrees because you'll get an exact answer in degrees. If you put it in radians, you'll get a crazy decimal. In degrees, you should get negative 45. But negative 45 is quadrant 4. Once we plot it, we know it's quadrant 2. So we're going to add 180 to that. It's really 135. 135 is quadrant 2. And then we need to change that to radians. 135 is not wrong. 135 is right. It's more common to see these written with radians, though. So I just wanted to get you used to to doing that. Say it again. 3 pi over 4. So as an XY point, as a rectangular point, we could label that spot as negative 3, 3. As a polar point, we can get to that exact same spot. The spot's not different. We just get there a different way. We get there by going 3 radical 2 units out on the 3 pi over 4 line. It's still taking us to the exact same spot. We're just getting there a different way. Like if I needed to get to Arturo's chair, I could climb up over the desk and go straight there, or I can go around the table. Either way, I'm going to get there. It's just 2 different ways to get there. I'd rather climb over the desk. So since it's 2 different ways to get there, we've got to describe those 2 different ways differently. And hopefully all these formulas are familiar. We've used all these formulas before just to do something different, but they're the same exact formulas. The only thing that usually ends up being kind of tricky is the angle and making sure it's in the right quadrant.
But could you figure out if for it to be 45 degrees since it has both the same?
Yes. Yeah, you could probably just look at it and see since the absolute value of those numbers is the same, it's exactly halfway in between, so it's got to be 45.
Yeah, that's what I did.
Yep.
When you did it.
Yep. Zero, negative 5. So where is 0, negative 5? Straight
down.
Straight down, 5 units. That is called a quadrantal angle or a quadrantal point. Yep. It's not in an angle. It's on the dividing line between quadrant 3 and quadrant 4. We can still go through with our normal formulas, but we can't draw a triangle for that. But still go through with your normal formulas. Okay? We're going to run into a problem with the angle. Because it's going to say divide by 0. But because we're on an axis, the angles are usually a lot easier. Yep, so this is our x and our y because the directions say convert this rectangular point to polar. So what they're giving you is an x and a y. The x and the y are the legs of the right triangle. Even though you can't draw the triangle for this one, you can still consider them the legs for the right triangle. R is the hypotenuse of the right triangle. It is possible for R to be negative, but it typically does not happen because R is a distance. R is how far out do I need to go on this particular angle line. With x's and y's, the negative and the positive indicate a direction, left or right, up or down. But with the r and the theta, we don't need r to indicate a direction because theta indicates the direction. R can be negative, but it usually doesn't need to be. R usually is just positive. So we need to go out 5 units. Now, when you set up your theta equation, remember theta is tan inverse of the y over the x. Now, if you try to do that, your calculator is probably going to tell you an error. And that's because we've got -5 divided by 0, which we're not allowed to do. So we just need to remember the negative y-axis is what angle? It's 270. And we also want to see this in radians, 3 pi over 2. So as a rectangular point, this is 0, -5. As a polar point, it's 5 units out on the 3 pi over 2 line. Now there are other ways to write that polar point. Polar points are not unique. So I just said a minute ago, typically r is going to be positive. R is allowed to be negative. If r is negative, that means we're going to go 5 units in the exact opposite direction of a particular angle line. So if I'm going out on the 3 pi over 2 line, what angle line am I going the exact opposite direction from? Pi over 2, right? 3 pi over 2 is the exact opposite direction of pi over 2. Does everybody see that? So I could also say this is -5 units out on the pi over 2 line. I am moving 5 units away from the pi over 2 line. So that's also a possibility. It seems like extra work to do something like that, but it is possible. Mathematically, it is correct. It's obviously not our first, most intuitive choice, but it is mathematically correct. All right, let's try to figure the negative out for this one then. So we could change it to a -r. What's exactly opposite of 3 pi over 4? 7 pi over 4. And you could look at your unit circle, or you could see what's exactly 180 degrees across from it on your unit circle. Or add 180 degrees is equivalent to pi. You could add pi to it. Pi is 4 pi over 4, so 7 pi over 4. So we're going 3 radical 2 units away from the 7 pi over 4 line. So negative r values mean move that many units away from that angle line, exact opposite direction. So the negative r values mean move away or in the opposite direction of that theta. We're going to do a couple of the opposite direction, then we're going to look at converting some equations. So this time they're giving us a polar point. They're giving us a r and a theta, and they want us to change it to an x and a y. So this polar point says to do what? Where is this point? Just verbally describe what it's telling us to do. It's in the first quadrant, because pi over 6 is in the first quadrant, and the r is positive. It wants us to go 3 units out on the pi over 6 line. So there's the pi over 6 line. We're going to go 3 units out on the pi over 6 line. So if I was to see where that put me on the x-axis and the y-axis, that would give me my x and y coordinates. Now the 3 I just went out on that line does not correspond to 3 units on the x-axis. That is a slanted 3. I am measuring a slanted distance of 3. That is not 3 on the x or 3 on the y. So to go from r theta to x and y, this is like going from magnitude and direction to components with vectors. X is r cosine theta, y is r sine theta. We've got the r and the theta. We're going to leave these exact though. So we need to know what cosine of pi over 6 and sine of pi over 6 that is. And if anybody needs a unit circle, I've got tons of copies of unit circles in my office. Pi over 6 is 30 degrees, yes. But we want to know what the sine and cosine values are there.
Cosine. 2 for cosine, and 1/2 for sine.
Cosine of pi over 6 was?
Square root of 3 over 2.
Mm-hmm.
And sine is 1/2.
So we get 3 radical 3 over 2 and 3 over 2. So as an xy point, we've got to do 3 root 3 over 2 out on the x-axis and 3/2 out on the y-axis. There's no other way we can write that with x and y. So the r theta, there is another way we can write it. If we can change the r to negative and flip the pi over 6 around backwards. But there's no other way we could write that with x and y. The x and y points are unique. It means there's only one way to do it. Negative 8 pi. Let's make a prediction first about where this is going to be. 90? Any other guesses? 80 degrees?
180.
180 degrees? Pi is 180 degrees. Any other predictions?
Oh, it's going to be 0 degrees.
It's going to be, why is it going to be 0?
Because it's a negative 8.
Because it's a negative 8. So pi is 180 degrees, but then the r is negative, which means move away from it. Exact opposite. When your r is negative, it means move away from that angle. So this is actually going to end up on the positive x-axis. This point is on the positive x-axis. So this one's kind of confusing to graph. You don't necessarily have to graph it ahead of time to do the problem. You can just jump straight into the conversion formulas. You can say x equals r cosine theta. Y equals r sine theta. Make sure your calculator's in radians. If you're going to type it in your calculator, if it gives you some crazy decimals, then you're going to want to look at your unit circle to help, because we want an exact answer. Issa, I know you already know the answer. Nope. Nope. 80. It's on the positive x-axis. Positive x-axis. I heard you say over there it's going to be on the x-axis. It's okay. I'll give you a chance to redeem yourself. So pi is to the left, but the negative says go the other way. So we go to the right. Okay? So that's why it's over on the positive x-axis at 80.
Since it was positive 8, pi be
At negative 80. So the xy point is 80. So negative 8 pi is the r theta, 80 is the xy. All right, you guys do this one really, really, really fast, and then we're going to go on to equations. This is an r and a theta, 12, 0. Okay.
What about that junction though?
So, all right, you had a chance to do it. All right, so tell me how you set your formula up.
12 cosine 0.
12 cosine 0, 12 sine 0, and x comes out to be 12, y comes out to be 0. So as an xy point, the answer is exactly the same, but it means something completely different. So in polar, it means we're going 12 units out on the 0 angle line. In xy coordinates, it means we're moving 12 units to the right, and we're not moving any units up or down. So it's just kind of a coincidence. But it can look kind of confusing. But all the points on the x-axis are like that. On the y-axis, the angle is going to be pi over 2. Or, actually, we could say, on the y-axis, we could say go negative units from the 0 angle. If we did negative units from the 0 angle, those would put us on the negative axis. So if we represented them with negative r's, they would be exactly the same in rectangular and polar.
So would negative 12, 180 be the same as 12?
Yes. Negative 12, 180 would be the same as 12, 0. Huh? Yes. Yep. What's going to be most useful for us is converting equations. Because there are certain equations that we're going to talk about here in chapter 12. There are certain types of graphs, and we're going to have a break in just a minute. I know. No, everybody's looking at the clock, not just you. There are certain types of graphs that are much, much nicer in polar form. Almost anything circular, or anything that has circular cross sections, is much nicer to represent in polar equations. Okay? The reason is because circles are not functions. We have x squared plus y squared equals radius squared. Those are not functions. We can't solve them for y. It would be y equals plus or minus square root of something, which is really nasty. And we'd have to separate it and write it as two separate functions and work them out separately. As a polar equation, though, because there's no restriction on the angle and we're using the entire circle, if we convert them to polar, we completely eliminate the theta from the equation. And circles are actually represented as polar equations with only one variable in them. Whereas in rectangular, they've got two variables and they're not a function. So anything circular or anything circles or circle cross sections are much, much nicer in polar coordinates. And eventually in chapter 13, we're going to be integrating these. So when we integrate them, we're definitely going to want them written as simple as possible.
Do you have like a spiral as a polar equation?
Yeah. Well, a spiral isn't a surface. A spiral is just a curve. So a spiral is going to be represented by a vector valued function. So a spiral is just a curve. But in chapter 14, we're going to do line integrals. But we're probably just going to have a day or two to touch on chapter 14 at the very end. But we'll talk about line integrals in chapter 14 at the very end. So it's going to be more helpful to us now that we've had some practice with those conversion equations is actually converting entire functions over from rectangular to polar. So anywhere we see an x, we're going to want to replace it with r cosine theta. Or anything we see a y, we're going to want to replace it with r sine theta. So you can replace individual variables, or you can replace entire chunks of the equation. And one nice big chunk that you can replace is x squared plus y squared. Look back at your conversion options. What would x squared plus y squared be equal to in polar? Almost.
No,
R squared. X squared plus y squared could get replaced with r squared because we said r is the square root of that stuff. So if you ever have the x squared plus y squared chunk in your function or in your equation, all of that together could be replaced with an r squared. So those two variables can get replaced with just this one. So that's why polar is nice we usually see x squared plus y squared in circles. And we're replacing two variables with one variable. If you don't have the x squared plus y squared chunk, you might have to just replace variables individually and then just try to simplify as much as possible. In algebra, when we're using the variables x and y, what variable do we usually like our equations solved for? Y. When we use polar, we usually like our equations solved for r. So in algebra, we learn if it's possible, we like our equations to be y equals a function of x. And in polar, we like our functions to be r equals a function of theta.
This is for
When we switch them over to polar coordinates. You can make polar graphs on your calculator as well. If you look on your calculator, under mode, the fourth list of options starts with function, but you can change out of function mode and put it in polar mode. The third option there after function is polar. And if you choose polar and hit y equals, what does it say? It says r equals. It says r equals. Look at your x button. What's the third option there? Theta. Right, bless you. Your y equals changes to r equals, and on your variable button, the variable, the third option is theta. So we like it as r equals a function of theta when we're in polar. All right, so we're going to start simple. Convert each rectangular equation to polar. The first one is x squared plus y squared equals 25. What is that? X squared plus y squared equals 25. What's the shape? Yes, that's already the answer. It's a circle. It's just a circle centered at the origin with a radius of 5. And Kirby's already got the answer for us. Whenever possible, replace an entire chunk. And it will go much faster. So whenever you have that x squared plus y squared chunk, replace it all at once. So x squared plus y squared is equal to r squared. So I'm going to replace the entire x squared plus y squared with r squared. And solve for r if I can. Now, when we solve for r, we don't have to do plus or minus. Okay? On the square root. Because the theta, since theta is missing, that means there's no restriction on theta. That means our theta is going to go all the way around. So I don't have to use positive r's and negative r's. Theta is going to take us all the way around and do all of them. So to solve for r, we got a square root. And one really important thing I want to point out to you here is we've taken this from an equation that has two variables to an equation that only has one variable, which is definitely going to be much easier to work with. And the fact that there is no theta in that equation just means that there's no restrictions on theta. All an equation is a restriction. An equation means we're going to use a collection of points that meets this restriction. And if theta is not included in that, that means theta has no restrictions. That means we can use every single angle on the graph. Theta is not in the equation. That means theta is not restricted. So we're going to go out 5 units from the origin along every possible angle.
Circle.
And it's going to make a circle. It's going to make a circle of radius 5. So anytime you have a variable missing from an equation, that means there's just no restrictions on it, because that's all an equation is a restriction. So, prime example of what I was saying earlier, a circle, much, much easier to work with in polar coordinates. It's just r equals your radius. R equals 5 is the polar equation for a circle. If you have your calculator with you, in the past, it's been very hard to graph circles on your calculator unless you use the draw function. You would have to put in like positive square root of 25 minus x squared and negative square root of 25 minus x squared into y1 and y2. From polar mode, you can just put in r equals 5 and draw a circle. Do zoom trig. Make sure you're in radians.
I don't know what that is.
Your screen is not a perfect square, so it's probably elongated.
Like that, elongated?
Hold on, I'll come over in a second.
I was gonna say, is it
Y equals 4x. What does this graph look like? It's a straight line. It's a straight line through the origin with a slope of 4. We don't see our x squared plus y squared chunk in this one, so we're just going to have to replace variables individually. All right. So what did we say that y is equal to? What's the conversion formula for y? R sine theta. And x is r cosine theta.
That's it.
We've got to do something to it.
Cosine theta minus sine theta. Like, you want to do something to it? What do you want to do to it?
We either need to solve for r or for theta.
Let's solve for r. Look at 1, 4. No, I don't. That gets rid of r. And 4 this after that about works. Can we solve for theta? Can we solve for theta?
We could solve for theta. Let me ask you this. both of those pieces have r and theta in them, okay? So we're going to have to get them together. Do I want to subtract this entire term over and leave a 0 over there? Or do I want to divide part of it over? We're going to divide part of it over, okay? If I subtract the whole thing and leave a 0, usually when we have something equal to 0, we end up kind of factoring and separating. And that sounds like it's going to end up way more complicated, and we're going to have multiple parts to this equation. That sounds like solving by factoring back in algebra class. We're not trying to do anything like that. We're just trying to isolate one of the variables, okay? So we don't want anything equal to 0 here. Let's just divide over part of that. Let's leave the 4 over there. Let's leave the 4. Let's divide over the r cosine theta. Tangent. Those guys cancel. The r's cancel. Sine over cosine is tangent. So we have tan theta equals 4. Theta is tan inverse of 4, which technically we could calculate. Make sure you're it really doesn't matter, I guess. Since we're in polar, we should probably be in radians. But as long as, I guess, we indicate whether we're in degrees or radians when we write our answer, it's correct either way. 1.33. The r is missing here.
So we just plug in data back into
That means it could be no restrictions on r. Remember, r tells us how far out we're going to go on that theta line.
So you can't really tell anything from these rectangulars. You just tell either how long it is or how far it is. You can't tell both.
We can. I've given you two very weird examples. We'll do one more. We need to have a break. I've taken up like all of class time doing this.
Huh? You took a one last time?
I've given you two really weird examples where they cancel out. So in circles, the theta always cancels out. In lines, the r cancels out. Because lines go forever in both directions. So there's no restriction on length because we need to go forever on a specific angle line. So r is missing because there's no specific length that we're going to go on that angle line. We're going to go forever on that angle line. And we're going to go forever in both directions, positive and negative. But we have to stay on that one particular angle line. So if we were to look at this graph real quick, and then we're going to do one where they both stay. So y equals 4x is a line through the origin with a slope of 4. What we're also saying here is that this angle in radians is 1.33. And we're allowed to go out as many units on it as we want. We can go out a half a unit, we can go out 10 units, we can go out 100 units, we can go -2 units, we can go -40 units. So that's why we also go down forever in the opposite direction. And that's what makes them have the exact same graph. I'll do something different. I want to change it. Can I change it?
Sure.
Just a tiny bit.
What's the meme of the month? Stabby now?
What?
Ain't like the new meme of the month, like this. Like something. Stabby.
Are you saying you're going to stab me?
No, not yet.
Recorded evidence doesn't say that too, so. Wait to go away.
I just changed it a tiny bit.
No, yeah, trying to be, yeah.
This isn't the same problem.
The graph has the same name.
Should we factor it?
No. Well, no. No.
I'm gonna factor it.
I suggest you don't.
Sorry.
Too late, man.
Always look for a chunk first.
I see no chunks.
Adam sees no chunks.
Or you
I see impossible.
can, I guess, you can do x squared equals r squared minus y squared.
Got to get rid of all x's and y's. So we don't want to do that. So we don't have the x squared plus y squared chunk. So we got to replace them individually. Okay?
R squared cosine squared.
Uh-huh. We want to solve for r if possible.
It's possible. It's not possible. It's not data.
Can't solve for data.
We just give up the whole.
Pretty much.
What's that teaching kids?
Impossible. Unless you give it to an offer.
At this point, there's not much more we're going to do with this equation. In chapter 13, there will be more that we do with it. In chapter 13, when we start looking at volumes and we start doing multiple integration, we might see where this graph intersects with another graph. So we might set them equal to each other, or we might see where this graph intersects the xy plane. So we'll see where it equals 0 or something like that. But for right now, we can't solve this for r because there's an r squared and an r. It's a quadratic equation. that's not going to factor, doesn't have a common factor. We can't solve it for theta because, again, it's a quadratic. There's a something squared with a theta and something without squared that has a theta. That's not going to factor. Might be able to play with it a tiny bit and change the cosine squared to a 1 minus sine squared. Don't think that's going to help us out a whole lot. I think it's just going to waste a bunch of time. There's really not much more we can do with this. But I didn't want to mislead you with the first two problems and make you think that, oh, one of them always goes away, because it doesn't. This one's still got both of them. And a lot of times there's not a whole lot you can do with them. Not every single one of the equations looks much nicer in polar. Some of them look worse in polar. So does a parabola have circular cross sections? Is a parabola made up of circles? No. No, we said it was the circles or anything that we could make like circular cross sections with somehow. Those are the ones that would be nice and polar. I'm gonna throw one more thing at you real fast. 30 seconds and we're going on break. Cylindrical coordinates. We're gonna take polar coordinates and we're gonna put it into three-dimensional space with some absolutely groundbreaking ideas. We're gonna throw a z on the end of it.
But how there's you, it's not actual.
Our theta will deal with the flat, and then z will make it come out. So the r theta will convert the xy, and then the z is just its own thing.
The z is not going to be any, so it doesn't convert to anything.
The z does not convert.
Awesome.
Z does not convert. The z from the old three-dimensional is the exact same z in this one. It's just the xy that converts to the r theta. Z is the same z. So polar and cylindrical, they're pretty much the exact same thing, but polar is like two-dimensional, cylindrical is three-dimensional. I think there's two Z's in Shazam. I don't care. So now I can spell it any way I want. All right, we have got to have a break.
Like Tyler, he had Duke win or something. They went out what first round? Second round. Wow.
A lot of 12.1 is review of lines and planes. We've already done a lot already with lines and planes, but chapter 12 starts talking about functions of several variables. The very first graph that we've seen in space is the curve, which is not represented by a three-dimensional equation, but by a vector valued function. So the first type of surface that we see in 3 dimensions is the plane, and that's actually the first equation that we see that has all 3 variables. So here in 12.1, they kind of review that just as a starting point for the first equation that has all 3 variables, x, y, and z in it. But then they also start to get in to some of the other basic types of surfaces and how we can figure out just by looking at the equations what they're going to look like. But there's a lot of review here in 12.1 of all the stuff that we've already learned about with the planes. And also lines written as vector valued functions. So we're not going to be able to, we don't have a whole lot of time left today, but we're not going to be able to get very far into 12.1. What I did want to tell you is there is another coordinate system that we're going to learn. We're not going to do it today, but there's another coordinate system we need to learn before we get into chapter 13 called spherical coordinates. And I'm going to save it for a few days. I'm going to let polar sink in a little bit. And then we'll do spherical. Okay? Yeah, it's like it's very similar to latitude and longitude. It's not exactly the same, but it's very similar. All right. So chapter 12 is functions of several variables. We'll talk about this for about 15 minutes. There's a symbol that you're going to see that you may have not seen before a lot in this chapter. And it's an R with an extra line in the front. It's all real numbers, but they're gonna throw a little superscript on it. Whoops. So you might also see R2. This means we are working with two number lines that can use all real numbers. So like an x-axis and a y-axis. So it's working with ordered pairs. So it's like the two-dimensional plane. Okay? So that superscript that you see on the R tells us how many axes we're dealing with, how many variables we're dealing with. What dimension, right? Oh, I didn't hear everything you said.
You said that's right.
I thought he just said what dimension.
Fourth dimension. That's right.
So this book likes to use this symbol a lot. Our last book didn't use this terminology at all, but this book likes to use it. So this number includes the independent variables and the dependent variables. So in R2, there's always going to be one dependent variable. Otherwise, it's not going to be a function. And then all the rest of them are independent variables. So there's one independent variable. And one dependent variable. In R3, which contains x, y, and z, there's only one dependent variable ever, and that's the z. Which leaves the other two, x and y, as independent variables. So we could have R6 be A, B, C, D, E, F.
You're getting a little excited.
I am getting a little excited. Let's see if we can see a pattern in the two above.
There's always, okay, A, B, C, D, E, dependent, F, dependent.
Yes.
There you
There are 5 independent variables, A, B, C, D, and E. There is one dependent variable, and that is F, the last one. Okay? So R12, I fully expected Adam to give me a nasty look. He's just not paying attention.
go. Go to surrender.
We're not doing
Oh, you
R12.
said R12?
I'm not- we're not doing it.
Oh, I'm sorry.
We're not doing it.
I'm good.
You're doing it.
I'm good. Whoa. I mean, we can watch.
Nope. Nope. So quick review of planes. That's the first equation that we see. That's an actual equation that involves all 3 of our variables in 3 dimensions. There are 2 pieces of information that we need to write the equation for a plane. Does anybody remember what they are? What 2 pieces of information do we need in order to write the equation for a plane?
Equation of a line on that now. There's what's in there somewhere.
Did you say length and width?
Yeah.
That would be to find the area for a rectangle. A plane goes on forever in every direction. And we want to know
It's not here.
a plane in 3-dimensional space could be at a particular angle, and it could go through particular points that would make it have a different equation than other planes that are at different angles and go through different points. But any plane in space actually would go on forever in every direction.
So you need a point P and a vector normal to the line.
Yes, we need to know at least one point that's on the plane. And a vector that's normal to the plane.
Which is also perpendicular.
Yes. And orthogonal. Any of those 3. So if we have point P, which we will call x1, y1, z1, and normal vector n, which has components a, b, c, there are 2 formats for the equation for the plane. They were very closely related. One of them is really just the basic setup, and then the second one is where we just multiply it out. So the definition for a plane are all the points where the normal vector is at a 90-degree angle to some other vector that connects with P, where Q is some random vector in space, x, y, z. So if we pick some, oh, that's not true. Q is some x, y, z in the plane. Q is some x, y, z in the plane that we don't know. P is some x1, y1, z1 in the plane that we do know. So Q represents any point in the plane. Any point in the plane whatsoever. We do know one point in the plane P. Vector PQ, we can get component form for that by doing the Q's minus the P's. And then if n is a normal vector to the plane, PQ is in the plane, and n is normal to the plane, what's the dot product of two normal vectors always going to be?
Scalar.
It's, a dot product is always scalar.
My bad. Oh, it's 0.
It's always going to be 0. So this is where the formula for, or the equation for a plane comes from. The equation for the plane is any point x, y, z in the plane that when you create a vector with P, its dot product with n is 0. So now if we create vector PQ, to create vector PQ, we do the Q's minus the P's. Now Q is just a variable vector. It represents any possible point that could be in the plane. So Q has the variables x, y, z in it. P has point values though. It's got coordinate values, x1, y1, z1. So what would the component form for PQ be? How do we find component form if we know the beginning point and the ending point? We do ending minus beginning. So I'm going to do x minus x sub 1, y minus y sub 1, z minus z sub 1. That's vector PQ. And then I'm going to dot that with n. And it will equal 0 because PQ is in the plane. N is normal to the plane. That is always going to be true. And the dot product of two vectors that are normal, the dot product of two vectors that are 90 degrees is always going to be 0. So PQ dotted with n. Dot product is where we multiply corresponding components and add the results. So PQ dotted with n, well, n has components a, b, and c. So this is going to be a times x minus x sub 1 plus b times y minus y sub 1 plus c times z minus z sub 1. And according to properties of dot product, that should equal 0. This is standard form. And if we were to go ahead and work out our algebra on that, it would be general. So I talked about this back in chapter 11. I didn't really talk about that dot product and where the equation comes from. We just kind of jumped into, here's the formula, plug in the numbers. But this is where the formula comes from and why the formula works. Now that we know a little bit more about dot product, hopefully we're a little bit more comfortable with it. We haven't done it in a while. We've done some other things since then. But technically, the plane is any point that you can dot with that other point any point that you can make a vector with that other point, and then when you dot it with the normal, it comes out 0. Last little tidbit, we're not going to have time for examples today, but last little tidbit, if you're ever asked to compare planes, like see if two planes are parallel, see if two planes are perpendicular, see what the angle between two planes are. So if you're ever asked to compare two planes, all you have to do is compare their normal vectors. Just see if the normal vectors are parallel, if the normal vectors are perpendicular, what the angle between the normal vectors are. Because whatever's going on between those planes, the exact same thing is happening between the normal vectors. And that's because of properties of geometry. Even if you're just given the general form for the planes, remember you can get the normal vectors from the coefficients. So if I wanted to know what was going on between those two planes, if I wanted to know if they were, it's two intersecting planes.
Oh, okay. Butterfly. I know what
It can be a butterfly. If I wanted to know what was going on between those two planes, so maybe like the angle between them or something,
I'm not even trying to tell that. I can't hear it.
the normal vectors for those planes would have the exact same angle between them. Do you remember back to geometry when you learn transversals and vertical angles and opposite interior angles and all that stuff? Kind of. Any of that sound familiar? No. This angle here is a corresponding angle to this angle here. They will always be exactly the same. So if you ever have to compare two planes and what's going on between two planes, whether they're parallel or perpendicular or just calculating the angle between them, you can always just pull their normal vectors out and figure out what's going on between their normal vectors. Because we've talked about previously how to figure out if two vectors are parallel or perpendicular, or calculating the angle between two vectors.